Okay, welcome back, and we're live. It does look like Eric and Andrew are going to try to get in through the Wi-Fi, but are going to be in and out. So I'm going to go ahead and get started with what we have. I think I'll just alternate between the two of you then. So starting out with, if I derive x to the n power, what's going to happen? Kelly? Perfect. I'll just do it this way. Okay. Kyle, if I derive f of x times g of x? Perfect. So here it is again. Kelly, quotient rule? Perfect. And Kyle, chain rule? Okay, so that's f prime of g of x times g prime. Should look like this. Kelly, if I derive sine, what will I get? Okay, Kyle, if I derive cosine? If I derive tangent? Okay, and if I derive secant? Perfect. Kelly, cosecant? Okay, and Kyle, cotangent? Perfect. Kelly, derive e to the x? The same, e to the x still. And Kyle, natural log of x? 1 over x, okay. Kelly, if I derive a to the x? Perfect. Which we know is right because if I plug in e to the x, then I still get e to the x times natural log of e, which is e to the x times 1, which is what we had for e to the x. Kyle, if I derive log base a of x? In this case, this is 1 over something. Okay, 1 over x, and then ln a on bottom. And then again, if I plug in log base e of x, which is the natural log of x, then that would be the natural log of e for my ln a, which would be 1. Excuse me. Kelly, how do we know if a function is continuous? Perfect. So if I want to write that in a formula form, it would look like this. So I've got the limit as x approaches c of our function. So that's our general limit. Should be equal to f of c. So that's what happens if I actually plug in the point. Kyle, how do I know if a function is differentiable? Okay, so there's a general limit for the derivative as well. You said 1 and 2. Do both conditions have to be true, or is it 1 or 2? So you gave me 2 conditions there. You said number 1, it's continuous, and number 2, the general limit of your derivative has to exist. Okay, so perfect. Okay, so both of these conditions have to be true. So the first part's the same as the last one. I have to be continuous, which means my general limit's equal to what happens if you plug it in. And my limit from the left of our derivative has to be the same as my limit from the right of the derivative. So that means our function would not be derivative at a cusp. So something that looks like this. Because my limit from the left of that derivative is not the same as my limit from the right, even though that point is continuous. Okay. Kelly, for El Hospital's rule, if I take a limit of a fraction and I end up getting infinity over infinity or 0 over 0, then what can I do? Okay, so our limit should be equal to the limit as x approaches c of f prime x over g prime x. So that's deriving the numerator denominator separately. Perfect. Which I could write like this. So our limit should be equal to the limit as x approaches c of f prime over g prime. Okay, inverse trig functions. I believe we saw this at the very end of pre-calc, but we haven't seen it in 3 months now. So I'm okay if you guys don't remember these. Does anyone remember derivative of arc sine? We did go through these, right? Okay, so if we haven't gone through these, then I can take a step back and teach these from scratch. If we have gone through these, then I can just flash answers. So did we go through these or not? Yes. Yes, okay, so we did talk about these. Okay, so I'm gonna flash. So for the arc sine, this is 1 over the square root of 1 minus x squared. And the way that we would have gotten there is through implicit differentiation and then solving for dy over dx. So I'm going to throw open a new page really quick. So what I want to solve is y is equal to the arc sine of x. So to undo an inverse sine, I can take the sine of both sides. This is the sine of y is equal to x then. Okay, if I derive the left side, what's going to happen? What's the derivative of the sine of y? Okay, cosine of y and then chain rule. Okay, dy over dx is equal to right side? 1. Okay, and this would be dx over dx, which you don't have to write because it will cancel. Okay, now our goal is to solve for the derivative, which is dy over dx. We need to get dy over dx alone. So this would be dy over dx is equal to 1 over the cosine of y. Okay, so now what I'm going to do is I'm going to go ahead and rewrite our equation using this line. The sine of some angle y should be equal to x over 1. Okay, sine is opposite over hypotenuse, so the opposite of this angle should be equal to x, and my hypotenuse should be 1. If that's true, how can I solve for this side, which I'm going to call C? Kyle, how can I solve for C? So I used SOHCAHTOA in order to build the triangle, but right now I need to solve for a side length. This is Pythagorean's theorem. If you want to solve for C, so how can I set this up? Close. I'm going to set this up again. Let's take a step back and we'll build your Pythagorean theorem again. So this is c squared plus what? Okay, and we'll solve for C. Okay, and then C is... Okay, so right now I have 1 divided by the cosine of y. Right now my cosine of angle y, based on my picture, if C is the square root of 1 minus x squared, my cosine of y should be equal to my adjacent divided by hypotenuse, right? So that would be my adjacent side, which is C, divided by 1, which would be equal to the square root of 1 minus x squared. So I can replace the cosine of y with square root 1 minus x squared into... get a different color really quick. Into our equation here. Okay, so that would give me dy over dx is equal to 1 over the square root of 1 minus x squared. Or the derivative of y is equal to dx over square root 1 minus x squared. Okay, any questions on what we did? Okay, so I do have handouts that I'll go ahead and pass out to the WeChat with explanations for arctangent and arcsecant. And I'll also, I think we'll be okay on time at the end. So if you guys want to go over those at the end, I can go through these too and improve the rest of these formulas. If not, then I've got the other formulas down here for arctangent and arcsecant. Okay, skipping ahead. Back to Kelly for intermediate value theorem. As long as our function is continuous on a to b, then the intermediate value theorem tells us that our function must do what? Yes, pass through all the x values or pass through all the y values? Okay, so you're right. Intermediate value theorem says we have to pass through it all of the outputs, that's all of my y values, at least once, as long as we're continuous. We can pass through all of these y values more than once, or even infinitely many times. But we have to pass through each y value between them at least once. Intermediate value theorem only requires that our function be continuous. It does not have to be differentiable. Okay, over to Kyle. For mean value theorem, our function must be differentiable. Again, on our interval between a and b, it says there must be some value c between a and b, so that's an x value, such that what is true? Okay, you can give me an equation. Yep. So f prime c is equal to, say one more time.
F prime c is equal to fb minus fa over b minus n. Perfect.
So if I wanted to say that in words, this is your derivative is equal to your average slope between these 2 points. So it's our derivative at point C is equal to the average slope between A and B. You could also say this in words, saying that your slope of the tangent line at C is the same slope as your secant line between A and B. Okay, any questions on anything from the first page of formulas? Okay, been jumping to the second page then. Kelly, what is the equation of a line that is tangent to f of x at the point AB? Okay, you're really close. That's f prime at what x value? F prime A, perfect. Okay, and then Kyle, if I wanted to change this to be the equation of a normal line instead of an equation of a tangent line, what would change?
Instead of f prime over a, you got -1.
Okay, which would look like this. So we're still at that point. Kelly, what is the formal definition of a derivative? Okay, so that's our derivative, f prime at, I'm going to call this c for now. So f prime c is equal to what? I'll give you a hint. The limit as change in x approaches 0 of something. Okay, not sure. It's been quite a while for this one actually. So this is the very start of pre-calculus, first or second week. But I'm gonna draw a picture and we'll see if we can get there. So I've got the idea of a derivative is that normally if I was getting a slope between 2 points, you would get your change in y over change in x, right? In this case, I want my change in x to approach 0. So I'm going to call this first point x, y, which in our case will be x, f of x. And I'm going to call this second point x plus a little bit. So that's x plus a change in x. And that means my y value will be my output at x plus a little bit. It's a language difference, but you're right. So this is going to be our change in y over change in x between those 2 points. And then if I subtract these x values, x plus change in x minus x, my x's will cancel. So that leaves me with just a change in x on the bottom. Okay, so what this really means is our derivative is the same thing as taking a limit as our change in x approaches 0 of our difference in our y's divided by our difference in our x's. If there is no change in x, then your average slope between the 2 points, because you didn't really move at all, will be a slope at 1 point instead of a slope between 2. So I am squishing this point into, I'm squishing the rightmost point into my leftmost point, and it will become 1 point. Okay. Let me get rid of all of my drawing here so that I can give a typed version. So here it is again. Our derivative at some point x would be equal to the limit as our change in x approaches 0 of my difference in my y's divided by my difference in my x's, which is really just a change in x. Okay, Kyle, back to you for Euler's method. Perfect. That change in y over change in x is really going to be our slope, so that's our derivative at that point. Usually you'll be given a differential equation, which would look like this, so lowercase delta instead of an uppercase one, which means a slope at 1 point instead of your average change in y over change in x. This dx, though, is actually a change in x, not a derivative of x for this side here. So I'm going to change this one up a little bit than what I had. This is a change in x times your derivative at that point. Okay, Kelly, over to you. If I integrate u to the n power u prime, what will happen? Okay, plus we didn't have any bounds, so I need one more thing. If I'm integrating any function and I don't have bounds, then I need a plus something. Plus c, perfect. And Kyle, this time I do have bounds. If I'm integrating a derivative from a to b, what will happen? Perfect. F of b minus f of a. So I've gone back from the derivative to the original function, and then plugged in your upper bound and subtracted your lower bound. If I wanted to do the same thing with u prime over u, what's going to happen, Kelly? Perfect. Kyle, if I want to integrate the area, if I want to get the area between two curves, so that's f of x and g of x from x equals a to x equals b. So in this case, f of x is my top function and g of x is my bottom function. What do I need to do? Okay. Okay. Dx, because, yep, so we're integrating in terms of x. Okay. Kelly, what is the average slope of f of x from a to b? Yes. So this one's pure algebra, change in y over change in x. If I want an average value, then I'll need calculus instead. So Kyle, how can I get an average value? Yes. So that's 1 over b minus a times the integral of f of x from a to b. So basically what we're doing is we're getting all of the, I'm stepping up, so I'm getting all of the area underneath our function from a to b, but then I'm dividing by how many x values that we had total. So if I've got my total accumulated numbers divided by how many numbers we had total, then I'll end up with an average. Total divided by number of numbers is an average value, right? Okay, Kelly, this method? Okay, that's okay. I'm going to give Kyle a shot, and then if he doesn't remember, we'll talk a little bit. So, Kyle, do you remember? This is a way to find a volume of a 3D shape. Okay, cool. So, what we're doing here is quickly draw a function. So here's y equals ln x, we'll say. What we're trying to do is I'm trying to take all of the area that's underneath this curve, and I'm going to spin it around our axis. So in 3 dimensions, I'm going to spin this area about our axis of rotation to create a 3D cylinder like this. I'll shade this part in black so that it looks 3D-ish. So that means we've got a couple things here. I've got a radius. I've also got a change in x that is infinitely small. And because that change in x is infinitely small, I can write it as a derivative. Infinitely small change in x. And because what we've really done in spinning this radius around our axis of rotation is create a circle. If I wanted to write the area of this shape, what would my area be? So the area of this white shape that I've created with my circle should be equal to what? Pi r squared, because it's just a circle. If I want to make it a volume, then I would multiply by my depth of that circle, which in this case is dx. So my volume is pi r squared times dx. And then if I wanted to keep changing what the radius is from a to b, so from a start point to an end point, then instead of just multiplying by r, I'm multiplying by changing r. So that would mean as x changes from a to b, I'm going to multiply pi times r squared in terms of x. And that would give me a volume, since pi r squared dx is our volume. If I wanted to cut a smaller circle out of this, so in this case I want to make our shape hollow by cutting out a smaller circle like this, a hole. Then in that case I would have pi r1 squared, and then I would subtract my second area, pi r2 squared, from the first one, and still multiply by dx. So my area would look like this: pi r1 squared minus pi r2 squared. And my volume would look like pi r1 squared minus pi r2 squared times dx. Okay, I've got a pi in both of these, so I can pull out that pi, which is a constant, which means I can take it outside the integral. R1 and R1 minus R2 squared are left on the inside, and I'm multiplying both of those by dx. So my final answer here would be R1 squared minus R2 squared times dx, which gives us our dis method formula. Okay, any questions on where this came from? Or the process I've got so far? I'm going to flash our dis method again. So here's what it looks like. I've got pi times the integral from a to b of r1 squared minus r2 squared dx, where r1, okay, start that back up. Okay, I'm just waiting on Kelly now. There we go. Okay, so dis method formula from the top again. So that's pi times the integral from a to b of r1 squared minus r2 squared dx, where r1 in this case is our longer radius. So that's our distance from our axis of rotation to our outermost function. Will I have space to do this? I think I will. Okay, where r sub 1 and then r2 would be the distance to the innermost function instead. we're using outer and inner instead of top and bottom because sometimes you're given a function that's on the bottom of the curve that you want to spin around instead of on top. So in this case, from the axis to the outermost function is the function that's furthest away from the axis, and from the axis to the innermost function is the function that's closest to the axis. The axis is whatever line you're spinning about. Any questions on our formula, what it means? Okay, let me get rid of my scribbles down here. Okay, so that was this method. We use this method whenever we're spinning around a horizontal line. We use shell method whenever we're spinning around a vertical line. So I'm going to go ahead and draw some pictures again. But new pictures this time. I'm going to take our function. So this is, again, y equals ln x. And I'm going to spin this function about the line x equals -1 for my axis. And we'll go from x equals 1 until x equals e. Okay, so in this case, because I'm spinning around a vertical line, the fastest way to do this would be shell method, because it allows me to not change my variables. So what I like to do is, I like to think of this as being an infinitely small box that we're going to spin around our axis of rotation to create our disk. So this ends up becoming a cylinder-like shape that is hollow on the inside. So something like this. Okay, then I've got a side that's facing us that looks like this. Okay, so from the top to the bottom is our height, which is really our difference in our y values. So that's y2 minus y1 of our two functions. In this case, the natural log of x and 0 were our bounds. I've also got a radius, which is my distance to my axis of rotation. Which in this case is our x value plus 1. And we've got an infinitely small dx, which is our distance that, it's like the thickness of this cylinder that we've created. Okay, if I was going to take that cylinder and I was going to cut it and unfurl it into a box, then my box would look like this. So I've got an infinitely small dx on this side. I've got a height, and I've got a width, which is really my circumference. The difference around distance around this circle in black. My circumference is 2 pi r. My height is my difference in my y values, which for us is natural log x minus 0. My change in x is infinitely small dx. My radius we said is x plus 1, so I can substitute that in here, and we would get our general equation. Okay, so in this case, for shell method, my volume is equal to 2 pi r dx times our height. I'm gonna rewrite that really quick. So I'm running out of space. This is my circumference times my height times my infinitely small width, which is my change in x. Okay, again, if I'm going to move all the way through this natural log x space though, creating a bunch of tiny cylinders and stacking them on top of each other to get the perfect volume, then I'm going to need to keep changing what my radius is and what my height is as we go. So that means I'm going to have to integrate and change this formula as I go from my start point A to my end point B, which for us is from 1 to E. So I'm going to integrate this from point A to point B. 2 pi is a constant, so I can pull that outside the integral, 2 pi. And I'm left with radius, height, and width, or RHW, where my W is dx, as long as you are spinning around a vertical line. Any questions on my setup here for volume? Okay, so for our specific example that we've created here, this would be 2 pi times the integral from 1 to e of our radius, which is x plus 1, times our height, which is my difference in my y values, or natural log x minus 0, times dx. It should give me the perfect volume for what would happen if I spun that shape we had originally in green here about our axis of rotation to create a 3D shape. It looked like kind of the inner ring of a donut almost. Okay, so let me erase our picture and I'll give our formula again. So my volume should be equal to 2 pi times the integral from a to b of RHW. Okay, I think that was Kelly, then Kyle. So Kelly, we're back to you. If I take the limit as x approaches infinity of f of x, and the growth rate is faster on the top of the fraction than on the bottom of the fraction, then what will my limit be? Okay, so infinity or negative infinity, depending on the sign. Kyle, if my fraction's growing faster on bottom, what will happen to my limit? Will approach 0. And Kelly, if our growth rate is the same, what's going to happen? Cool, okay, so this is going to be the fraction of our coefficients. Normally it's of the largest power. I'm going to write just fractions of the coefficients. So this is really the largest growth rate, which will make this a little bit more general, so that if we're dealing with logarithms or exponents or something that's not a polynomial, then this will still hold true. For example, if I had something like this, the limit as x approaches infinity of e to the x over natural log x. Because exponentials grow faster than logarithms, I know that my top is growing faster. So this should approach either positive infinity or negative infinity, depending on the sign. If I plug in positive infinity right now, I'll have positive infinity over infinity. So this is approaching positive infinity, since my signs are both positive. Okay, if our growth rates were the same, so let's say this is e to the x over 4 times e to the x, plus 3 plus 7. Okay, right now, as I get bigger and bigger and bigger, closer and closer to infinity, my 3 and 7 are going to matter less and less and less, right? I'm only concerned with which term is my fastest growth rate. And right now, exponentials grow faster than constants. So I'm only concerned with my exponential terms. My coefficients are 1 and 4. So I'm going to approach 1/4. Since my powers were the same. Growth rates were the same in this case. And then if my growth rates are faster on bottom, so natural log x over e to the x in this case, and limit as x approaches infinity. Exponentials grow faster than logarithms, so this will approach 0. Okay, Kyle, back to you. If I have a left-hand Riemann sum and our function is increasing, will we overestimate or underestimate the curve? Okay, our function is increasing, and I'm using a left-hand Riemann sum, which means I'm going to get my heights from the left-hand side. So my estimate's going to look something like this, which will underestimate the curve. Okay, really all 4 of these blanks that I have filling in are the same question, just asked different ways. So I'm going to go ahead and flash answers here. Yep. We're going to underestimate as long as we are increasing with a left-hand Riemann sum, but we'll overestimate as long as we are decreasing with a left-hand Riemann sum, which I'll show again. If I'm decreasing, I'm going to use a left-hand Riemann sum, so getting my heights from the right, then I will overestimate. But if I'm increasing, then I would underestimate. Okay, but if I'm using a right-hand Riemann sum, it's reversed. If I'm using a right-hand Riemann sum and our function is increasing, so this means heights from the right-hand side, then I will overestimate. If our function decreases and I use heights from the right-hand side, then I would underestimate. Okay, any questions on these 4? Oh, okay, and Niles just joined us, so I'm going to throw him in for this last one. I want you to order the following function types from the fastest growth rate to the slowest growth rate. So which of these, constant, exponential, factorial, logarithm, polynomial, sine, or cosine, will grow the fastest? Okay. So constant is my slowest. Draw. Okay, and you said exponential is faster than that, so okay. So far you've got constant. What else do you think is slow? Okay, logarithms are pretty slow. Anything else here that's slow? I would say yes. So our sine function, it does grow, but all of its growth it loses, right? So this doesn't really grow. Or all of the change, it reverses all of its change. So in this case, constants don't change at all, so that's the slowest. Sine does change, but it loses all of its change, so that's my second slowest. Okay, and you said logarithms should be next because they grow, and they do grow infinitely, but they grow super slow. Okay, then I've got faster ones out here. Which do you think grows faster? Exponentials or factorials? Okay, let me give an example really quick. So this is exponential is like 4 to the x, and factorial is 4 exclamation point. Or, sorry, x exclamation point. Okay, so 4 raised to the x power would be x number of 4s multiplied together, where x factorial would be every number underneath x multiplied by itself. Okay, so in this case, factorials are actually the fastest growth we have. As you approach infinity, if you're multiplying infinity times infinity minus 1 times infinity minus 2 times infinity minus 3, you're going to end up with a larger number than just 4 raised to the infinity power, which would be 4 times itself infinitely many times. Do you understand why? Let's say if x was 100, I'm just going to write the first 4 terms. So this would be 4 times 4 times 4 times 4 would be the first 4 terms of our 104 terms that I would have to write for this. Versus for my factorial, this would be 100 times 99 times 98 times 97. So my first couple terms are much bigger than my first terms that are only 4s. And even if I pick the number that's much bigger than 4, because I'm going to infinity when I plug these in, my fastest growth rate is still going to be the factorial. Okay, back to Niall. For our last two, which one's faster, exponential or polynomial? Okay, you're right. Exponentials are faster than polynomials. It is possible to have a decreasing part with a polynomial, where if we're going to infinity, you're not going to see that in the exponential. Just in general, though, if you've got a variable raised to a constant, then you're limiting how much that you're limiting the number of multiples that you have. Where if you've got a constant raised to infinity, you're not limiting your number. Does that make sense? So this one would be infinity times infinity times infinity, where this one would be 4 times itself infinitely many times. In the infinity times infinity times infinity, I've really got, if you want to think of it this way, 3 constants that you're multiplying together. Where in this one, I've got a constant I'm multiplying infinitely many times. And multiplying anything infinitely many times is going to grow faster than multiplying a set number by itself 3 times. So in pre-calculus, we had a mnemonic you guys created for me. So that was feed elephants peanuts, love someone cool. or maybe that was a class before you, I can't remember, but if it helps you, great. If it doesn't, that's okay too. I'll flash what all of these are. Okay, so that's it for formulas. I'm going to go ahead and drop these in the WeChat really quick. Oh, get rid of my extra drawings. Oops. It looks like a lot. I think you'll find you already know the vast majority of these. Okay, so the rest of this, we've got about 27 minutes left, is what the second half of our quiz is going to look like during week 1. So I'm going to have a handful of unit circle questions, which will look something like this. So I'm going to give you either arc, sine, cosine, tangent, secant, cosecant, cotangent at some angle on some interval. So I'll show you how to work these really quick. So this says, yes. Yes, I'm planning on the last day of the first week. We'll quiz out of our, we'll have our weekly formula quiz, and we'll have some unit circle related rates questions that'll look something like this. So format should be the same. Okay, so I've got the arctangent of -√3. So that means my tangent at this angle, the tangent of some angle, should be equal to -√3. Tangent on our unit circle is sine over cosine. So that means I have some sine value divided by some cosine value that equal -√3. So for unit circle values, that would be a -√3 over 2 divided by 1/2, or positive √3 over 2 divided by -1/2. So I'm looking for places where sine is equal to -√3 over 2, or sine is equal to positive √3 over 2, and our signs are different. Okay, can anyone give me an angle where the signs are different and the sine is a magnitude of √3 over 2? So sine is alongside, and the signs of our x and y value are not the same. Do you mean 30 degrees? Okay, so at 30 degrees, my sine would actually be a short side, so the sine would be 1/2. Tangent is sine over cosine. Okay, so not 30 degrees, no? Okay, I'll give another hint. At 60 degrees, our sine would be the √3 over 2 for our long side. However, in this quadrant, both x and y are positive. So that would not be what we're looking for, because I need sine divided by cosine to end up as a negative. Okay, at 120 degrees, so that's at sorry, here. 90 plus another 30 should be good. Okay, they did give us bounds in radians. So in radians, what is 120 degrees? 2 pi thirds. Okay, so that's 1. 2 pi over 3 is okay. Right, my next angle, where my signs would be different, since in our quadrant down here, both sides are negative. I'm going to end up with a positive root 3 for my tangent, so that's not going to work. So I need this angle down here, where my sine is still alongside. So that's at 5 pi thirds. Okay, I'm going to draw our unit circle again, really quick, just for practice. Okay, so what I'm going to do is I'm going to split this up into 6. So I've got a rough circle. If I want to split up my pi into 6 evenly, so this would look something like this. And then I can continue those lines through the opposite side. Okay, a little rough on my part, but something like this. So this would be pi 6, 2 pi 6, which is pi thirds, 3 pi 6, which is pi halves, 4 pi 6, which is 2 pi thirds, 5 pi 6, which doesn't reduce, 6 pi 6, which is pi, 7 pi 6, 8 pi 6, which is 4 pi thirds, 9 pi 6, which is 3 pi over 2, 10 pi 6, which is 5 pi thirds, 11 pi 6, which doesn't reduce. Okay, whenever I have a long side, our long sides always have a magnitude of square root 3 over 2. Our short sides have a magnitude of 1/2. And our even sides, which only happen at multiples of pi fourths, which I did not draw for this one, would have magnitudes of square root 2 over 2. So in this case, if our sine, which is our y value, is a long side, so that would be here at pi thirds, here at 2 pi thirds, here at 4 pi thirds, and here at 5 pi thirds. Redraw that line again. Okay, then our magnitude of our y value will be longer than our magnitude of our x value. Okay, any questions on our unit circle so far? Okay, so our interval goes from -2 pi to 2 pi. So far we've gone one way around the entire unit circle, like this. And we caught the two angles that satisfied our conditions, where sine was alongside, and the sines of x and y are different. However, if I want to go back to -2 pi, I will also pass two angles again. So on my way backwards from 0, this would be -1 pi thirds, or if I want coterminal angles, 5 pi thirds minus 6 pi thirds is 2 pi, would give me -pi thirds. And coterminal of 2 pi thirds would be 2 pi thirds minus 6 pi thirds is negative 4 pi thirds. The 2 times that I would have passed those angles again on my way backwards to negative 2 pi. Any questions on how we got these angles? Okay, so the way that I would grade this is you would get partial credit for however many of these that you had in there. So if you gave me negative pi thirds, 2 pi thirds, and 5 pi thirds, but you did not give me negative 4 pi thirds, you get 3 out of 4 points. Okay, I'll try the next one. I'm looking for where is my sine equal to 1/2 between 4 pi and 5 pi. So here's my unit circle again. If my sine is 1/2, that means my y value is a short side. So that's going to happen here and here, where my sine is a short side, at pi 6 and 5 pi 6 on my normal unit circle. But my normal unit circle only goes from 0 to 2 pi. So what I'm going to do is I'm going to take those two angles, pi 6 and 5 pi 6, and we'll get coterminal angles to those that are bigger than 2 pi, and we'll keep going until we're between 4 pi and 5 pi. So Callie, over to you. I want angles that are coterminal to pi 6 and 5 pi 6. That would be on my next rotation. Okay, so to get coterminal angles, you can either add or subtract 2 pi. So right now, if I add 2 pi to pi 6, what will I get? Perfect. Pi 6 plus 2 pi. 2 pi is the same thing as 12 pi over 6 is 13 pi over 6. Okay, do the same thing with 5 pi 6. (17 pi over 6). Okay, so I went from 0 to 2 pi, gave me pi 6 and 5 pi 6 that were okay. And then from 2 pi to 4 pi, my second rotation, gave me 13 pi 6 to 17 pi 6. Unfortunately, that's 4 pi, so that's actually our start point, is right here. So I need to keep going for another value. Perfect. Okay, and now I just want to make sure that I didn't go too far. So 5 pi is the same thing as what over 6? So our bounds were 4 pi to 5 pi. Okay, so that's 30 pi over 6 is my ending bound. And my starting bound is actually 24 pi 6. Okay, so I only need these two. Okay, because my next one would be 37 pi 6, which is too much. Okay, so that's 25 pi 6 and 29 pi 6 are inside my interval. Okay, any questions on what we did? Okay, next one. I'm looking for where is the secant equal to -1. Secant is 1 over cosine, and the cosine is -1 only at pi. Okay, so I know pi is okay. I'm going to jump to Nile. Nile, our bounds go from -pi to 3pi. And those bounds are included. So what other angles are coterminal with pi? Okay, I think we actually lost Nile. I've got a weird symbol by his name. I'm going to jump over to Kyle. -3pi/2 would be here. So that start at 0, go backwards by 3pi12. So that's not the same point. Anytime you want a coterminal angle, you can add or subtract 2pi. Okay, -pi is okay, and that's the end bound of my interval, so I don't need to go any further than that. But I've got one more that's inside -pi and 3pi. 3pi itself is okay. Okay, and that should be my answer. -pi, pi, and 3pi. Okay, over to Kelly. I'm looking for the what angle the cotangent would be equal to 0. My cotangent is the same thing as cosine over sine. So I'm really looking for where is the cosine equal to 0. Not 2pi. Okay, at 0 and at pi and at 2pi, my x value is not 0. Pi/4 would be here. Okay, so he said pi/4. Pi/4 would be here, I'm afraid. Okay, pi/2 and 3pi/2, perfect. Okay, so pi/2 and 3pi/2 are okay. My interval that is okay goes from -2pi to pi. -2pi is one rotation backwards. I'm just going to mark the angles that are okay right now. So this is the angle we want is here or here. And you gave me pi halves and 3 pi halves. Okay, one of those is okay because I can go forward to pi and then I'll have to stop because that's the end of my interval. So that first one, pi halves, is okay. Okay, but I need a couple more that are coterminal with these two before that in order to get backwards to negative 2 pi. Perfect. And that would get us back to the first point at negative pi over 2. Went backwards by pi over 2, and I hit the same point as 3 pi over 2. Went backwards by 3 pi over 2 from 0, and I hit the same point as our original pi halves. Okay, if I keep going from there in order to get to negative 2 pi, then I'll stop before getting to my point again. So these are the only ones that are okay. If you can't see that that's where you should stop, I can rewrite negative 2 pi to be over 2. So that's negative 4 pi over 2. And this one would be 2 pi over 2. So I know I have to cut off between 1 pi over 2 and 3 pi over 2. And I know I have to cut off between my negative 3 pi over 2 and my next point, which would be negative 5 pi over 2, is too much. Okay, so my answer should be negative 3 pi over 2, negative pi over 2, and positive pi over 2. Okay, any questions on our unit circle stuff? Okay, so this is the format that I'm going to be using for our unit circle quizzes going forward. I've got an example of a previous year's week 4 quiz that I posted into the chat so you can get an idea for format. But our week 1 quiz will look just like this. Exactly like this with different numbers. Oh yeah, I was going to pull up this timed quiz. Okay, so the goal is eventually to get to something like this as a timed quiz, where I can really quickly time you on unit circle values, as well as do a couple things with intervals. You can see my times previously. Previously by week 4, we had gotten to the point where we could do about 1 question per minute for these. So I'd time these at 10 minutes and do these towards the end of the week. And then a little bit less time if you guys are just doing straight. Give me a unit circle at this angle instead of giving me multiple angles within an interval. Okay, so the rest of this I'm going to leave for homework, although I will come back for office hours if you guys need help. The rest of this mock quiz, I have one line that you're giving tangent to a point. So you use your tangent line equation that you guys gave me in your formulas in order to solve this one. I will say I've got a crazy 3-function part for this y value. Don't just derive this first, simplify this first. I guess I'll go ahead and do that part with you guys. I've got cosine squared, cosecant, which is the same thing as 1 over sine, cotangent, which is cosine over sine. So if I wanted to simplify this, I would take one of these cosines and move that here. So that would give me cosine x times cosine over sine, which is cotangent, times another cotangent. And now you've only got 2 parts for your y value instead of 3 parts. And now you can derive this using product rule. It's almost always easier if you can simplify before you derive than simplifying after you derive. Any questions on how I simplified this? Okay, and then once you derive this, you'll have to plug into your equation here. In order to get your point, you would plug in pi-thirds into your original problem. In order to get your derivative, you would plug in pi-thirds into your derivative, which is what you would get with your product rule. And you'll end up with a tangent line to the point. Okay, all of the rest of these are related rates problems. Cx, y. Okay, I think the rest of these are good. Oh, I did have a picture. I was just cutting it off. Okay. So for these related rates problems, you're going to set up an equation and then derive those implicitly, and then plug in everything you know and solve what you don't know. Any questions on what's going on for the homework? All right. Thank you guys very much. I'm going to leave, I think I already did leave, all of the solved formulas here in the chat. I did. Okay. So you've got a blank form that you can use for practice. So what I would do is I would go through all of the formulas with your blank sheet. Try your best to fill in what those formulas are, check against the answer key, and then just study the ones that you didn't get your first time around. So maybe make flashcards of those or something, either index cards or a sheet of paper that you can flip from one side to the other and test yourself over the next week or so. That way when we go to test on these on either the Thursday or the Friday when we come back, depending on whether you guys end up being A day or B day. So that'll be September 3rd or September 4th, I believe, when we're back in school. You guys will be ready for your formula quiz. Sorry, go ahead. Right. So for your week one quiz will look exactly like the week one mock quiz that I've posted here. So we'll do the formulas and then we'll start on the mock quiz. I don't know that we'll finish the rest of the mock quiz on that Friday or Thursday. If we take the whole class period, we will. If I take time to review beforehand, we probably won't. So if we don't have enough time to finish, then I'll take the formulas. And you guys will have more time to review your related rates and unit circle stuff before I actually take those up. Homework is just the rest of this this mock quiz. So I'll post that to the chat as well. Homework the rest of the week one mock quiz and the quiz on September 3rd or 4th will look identical with different numbers. Formulas will be exactly the same. So you can use the answers posted here to study. And again, we'll have office hours on Thursday if you guys have any questions. You have a lot more formulas than the AB class does, because we kind of need to get through all of AB before we can start with BC. So your formula quiz kind of looks like what AB's quiz will look like at the end of the year, as far as formulas go. But your related rates are the same that AB is doing right now. Your unit circle might be a little bit more advanced than what they're doing. Okay, thank you guys so much for coming, and please go ahead and try these so you've got questions for Thursday. Goodbye.